iOS Sandbox means. And I'm pretty embarrassed to say that I didn't even know what iOS Sandbox is. He gave me some directions about how to start researching it, but we didn't have a lot of information at this point. But one thing he did tell me is that there is an old tool that did this decompilation, which called Sandblaster. So today I'm going to walk you through my journey from not understanding the importance of this task to completely believing why do we need to invest time in it. So my name is Yarden, I'm an iOS security researcher. I'm working at Cellebrite for 7 years. I started as a decoding researcher, and for the past 3 years I work in iOS. My goal here is to provide you with the information I was missing when I started with this project, and to share with you why I believe it's a must tool for all iOS securities. So we will start by understanding the iOS Sandbox. We will continue with what are the benefits for us. Then we will uncover the unique file format for the iOS Sandbox profiles. We will see Sandblaster usage, what its main challenge and how we managed to overcome it. And we will wrap it up with shortly review the changes done in iOS 18. So the iOS Sandbox is a security mechanism implemented by Apple that actually makes our life much harder. They are well known in integrating very complex security mechanisms to enhance the protections of their system. The Sandbox is designed to protect system resources such as file systems, XPC services, and system calls, and it's implemented all the way through the kernel. Sandbox profile represents a set of rules, and by understanding these sets of rules, can significantly aid identifying vulnerabilities by allowing researchers to focus on areas they are most likely to succeed. Imagine that you're working on an exploit, developing it, testing it, just to understand that the Sandbox eventually blocking you. We can eliminate this trial and error process and quickly determine if the strategy is viable or not, just by understanding the Sandbox rules. Also, different processes might have different Sandbox profiles, so by analyzing this Sandbox profile, you can make a calculated decision. So the end goal here is to decompile the Sandbox profile. What do I have? I have an all implementation of a decompilation tool called Sandblaster. As stated in the README, Sandblaster is a tool for decompiling binary Apple Sandbox profiles. Apple Sandbox profiles written in SBPL, which stands for Sandbox Profile Language, and they are compiled into an undocumented binary format. Sandblaster is a tool that reverses the binary formats profiles into their original SBPL, and it supports up to iOS 11. We are now in iOS 18. When I started working on it, it was iOS 16 and almost 17. So what is the first thing that you'll do when you need to add addition support to an existing tool? You run it. So I've continued reading Sandblaster README, and I saw that for running it, I need to extract Sandbox data. Also stated in the README, Sandbox profiles are extracted from the kernel Sandbox extension. We have here a usage example, also taken from the README. It gets 3 arguments. One of them is the output folder, so we're okay. And we are missing the other 2 arguments. One they call SBOP, and one that they call Sandbox bundle. So the profiles that I need to parse reside in the kernel Sandbox extension, and they are in a binary format. They get referenced from a function called hook policy init, which is a function that initializes the profiles. If we will look at a part of this function, we can see some panic string that says fail to initialize platform profile. Now we know we're in the right location. So right above this Panic string, at the top of the picture, we can see pointer points to the con section of the Sandbox extension, which points to a binary data blob. A little bit below it, we can see something that looks like a size. So now we are able to extract the Sandbox data. We have one argument that Sandblaster needs. Now we need to get the second argument, the one they call SBOps. So SBOps stands for Sandbox Operation. They are the system call that the Sandbox policy is restricting. So to find them, I just need to search one of these operations. I found this operation list. It also resides in the kernel Sandbox extension. Its file changes from version to version. So now we have all what Sandblaster needs in order to parse this profile. And actually, I really wished that Sandblaster will work out of the box, but it was far from usable because the file format has changed dramatically. It was an amazing solution up until iOS 12, and now we need to make it work to iOS 16 and above. But it's not that simple. Although Sandblaster is an amazing starting point, it needs some adjustments. But another good thing in it is that Sandblaster is doing an amazing job in parsing the complex features in this file format. So if I'll just manage to read the file structure, the entire parsing process should work. So again, the iOS Sandbox profile represents a set of rules. We have here an example. We have, if we want to run dynamic code generation, we need to have dynamic code signing entitlements. Entitlements are key value pairs that define the permission granted to a process. Without it, the Sandbox will block this action. So the goal is to get from the binary format into this readable set of rules. There are two approaches that I used in order to parse this profile. One is to compile a Sandbox of my own, and the second one is to locate the parsing process in the kernel and reverse engineering it. Each of the approaches serves a different goal. By compiling it, I can test specific scenarios, but reversing the kernel can provide me a more comprehensive understanding of the parsing process. For example, by analyzing the kernel, I discovered that there are three types of format. A platform profile, which the entire system runs under it, built-in collection, and protobox collection. Those have different types and parsed a little bit differently. Also, I could see that the platform profile gets evaluated before the built-in collection. I've also discovered that the Sandbox is parsed and evaluated dynamically. And I saw some key functions that involved in this process, such as Sandbox evaluate that calls evaluate one operation and then eval, which they play crucial roles in evaluating and determine the actions to be taken. So let's dive into the file format. The file structure from several sections. The header section, which have an essential information about the profile, the operations section, which represent the list we provided earlier to Sandblaster of the system call that it should restrict. They are pointing to the operation node, which are the actual rules that determine if an action allows or denied. And they are using some strings and fixed values from the literal section. If we will zoom into the header contains type. For example, the single profile, like the platform profile, or bundles of profiles, like the collection, and a count of the operation nodes in the entire file, and operation count. We have here a small rule that I'm going to compile, and so we can see it in binary format. So it's the same example as I saw before. We have an operation which is dynamic code generation. which gets denied if we don't have the dynamic code signing entitlement. So we can see here the compiled format. The orange part is the number of operation nodes we have. You can see the operation nodes in the blue part. Each operation node is 8 bytes long, and just to tell you, we have here 3, because one is for allow, one is for deny, and one is for checking if we have this code signing entitlement. The green part is the number of operation, and the gray part is the table of operation pointers that each of them points into an operation node. I know, a lot of operations, but we will make it happen. So the purple one that is marked stands for dynamic code generation. I know it because it's in the same index as it in the list we served to SandBlaster. So the purple dynamic code generation points to node 0. Node 0, operation nodes are like decision points. So for instance, node 0, if the rule in node 0 matches, go to node 2. Otherwise, go to node 1. In our case, node 2 is allowed and node 2 is denied, but it can be much more complex, and it will get going until it gets to some decision. Now let's talk a little bit about collections. Collections are essentially bundles of multiple profiles, which each profile has his own set of operation table. They are also initialized in hook policy init, and they have a different type. Let's say we have a collection profile, includes profile for process A, process B, and process C. When we decompile the collection profile, we will get a profile for process A, a profile for process B, and a profile for process C. Now, if we zoom in into the profile section, we will see that we have this operation table for each profile. This is the gray part we saw earlier, and they come one after each other. We also have here a pointer to a name, which is the name of the process that is associated with this profile. Okay, so we parsed the profile, we are done with it. We are getting the decompiled sandbox in SBPL, and even though it looks readable, trust me, it's not readable at all. It's manageable when we have a really small rule, but when it gets a little more complex, it becomes impossible to read. It got into a point which this tool was pretty unusable. So then we started to think of a solution. How can we make it easier to read? So that's where my colleague came with a suggestion. These rules are only a set of if and else. So what if instead of writing it in SBPL, we will write it in C, compile it, and then decompile it with a decompiler of our choice. So we implemented it in SandBlaster, leading to this result. Each operation is a function that returns allow or deny. That way you can read basic C code and follow the rules easily. This decompiled output is way easier to read than the other one we saw before. I was happy and all, it was much easier for everyone, but then I started to get questions about how can I extract the sandbox profile from kernel. If you remember, it wasn't an easy task if you don't really know how the sandbox mechanism works. So one of SandBlaster users wrote a tool that automated this entire process, downloaded the requested kernel, extracted the sandbox from it, and run SandBlaster on this requested sandbox. This was and is my main goal when releasing this tool and talking about it here. I wanted that the community will be able to communicate with each other, to contribute code, to improve each other's skills. But then iOS 18 was out. It was not a priority for us to parse the iOS 18 profiles, not until it got necessary. Because let's face it, it's not as exciting as finding vulnerabilities. But I'm sure you know that it's really important to invest in your tooling, so we did it anyway. Let's review in short the changes introduced in iOS 18. So another collection profile has been added, which is called Autobox. It looks like just a name changing for Autobox profile. Also, the profile format changed a bit, of course, like almost every version. But the more important change is that they've added 2 more actions. So now instead of allow and deny, we have allow, deny, delegate, and Autobox. Also, in collection profiles, now each profile has a base profile. Most of them has the same base profile, which is baseline, but some of them are not. These show how Apple constantly improving themselves, which makes us improve ourselves and hopefully collaborate with each other. There are so many things. I want to understand this mechanism. I want to understand how Sandbox extension work, Sandbox state layer, app sandboxing. I want to make Sandblaster as easy to use as possible, which is way easier when the community is helping. I will keep researching it, and I invite you to join me, play with this tool, and share the insights when you have. I personally really love this project, and I believe that there is a lot more to learn from. I would like to say thank you first to the owner of Sandblaster, also to my colleagues, Leo that implemented the C output, and Daniel Yuval that contributed to this project, and also Blacktop and IPSW, which is a great example of an amazing tool. I will publish in the next week or so Sandblaster support for iOS 18, so stay tuned. This QR code is for Sandblaster repo, and I will publish on my Twitter some resources if someone is interested in reading more. I hope you enjoyed my talk and I have managed to give you some head start for those who want to research iOS Sandbox, and mostly to give you the information I was missing when I started with this project. There is a lot more to research and talk about, but this is all for this time. Thank you very much.
I do have perception. Okay. Major changes. I guess one of the files in there are hurdles that I implemented, like the actual initiative from it was like I think about a state. It was like 9% happening. Pretty bad. Some sandbox but actually later it's like data set. Red text. I remember like this one I had like just to put green and then there was 5 or 6 after without like and updates on my text layer and then
I thought it was okay.
Well, so I guess you have to understand that, like, so they said, like, the SPPL, it's like, it promised the syntax of this program, and then the primary is like that. And so it just like I know I had issues where Apple started like optimizing the decision trees. So if you had like two
Yeah.
options. So for instance, like you might disallow for video files where it's just like that and so like that's well, so
They're not. They're operating under.
yeah, I've been, but a long time ago, it used to
Wait, we haven't decided what's going to happen. Oh, I probably will. Okay. I'll talk. It's like a. We just like accomplish it. It's like a project. Nothing this week. Or anybody for that matter. This is going to be a project that we accomplished. Yeah, for the submission.
come and bring a bunch of about to die, like hot. Yeah. I think so. Pretty much everything's wrapping up. Yeah.
I got the impression it was like you role play as if you were like making decisions for
You could have let it cut.
No.
the North Pole will not tolerate these aggressive actions.
Be brave. Honestly, we're meeting is pretty fun. Like weird high level.
Just a message.
So the one time that I run it, it was really abstract. We just had teenage, something.
All right. Everybody, this is like a cast party for what we do in the shadows. It is with great pleasure that I introduce to you Travis Goodspeed, who is going to talk about building a modern assembler. Travis.
Howdy, everybody. Quick show of hands. Who here uses assembly language? Read or write? Awesome. Highbrow audience. Who here prefers x86 assembly language to anything else? Okay, we have 2 or 3 idiots here. Yeah, you think you're wrong, and the rest of you is no. x86 has a lot of complexities to it that do not apply to any other machine language I have ever seen. x86 has prefix bytes. These are used for things like repeating an instruction when you're doing a string operation or overriding the segment register. MSP430 kind of added that later, but by and large, no other architecture has prefixes to instructions. Most of them begin with an opcode. x86 also has this mod RM field, which is in the middle of the instruction. When you start looking at comparing your assembly language to machine language, you have pretty regular fields at the end, and you have an opcode at the beginning, and this mod RM sits in between them. And it has variable length, depending upon what addressing modes you're using, which means that not only is your opcode not at the start of the instruction, and not only do you need to relatively address fields from the opcode, which again is not at the start of the instruction, but also you need to relatively address them from the end of the mod RM field, which is itself varying length. And this is bonkers. If you did not have those 2 features, the prefix bytes and the mod RM field, an assembler becomes a lot simpler to make. When you have a project, in my case, I was writing this book on microcontroller exploits. And I had all these cool exploits in here, and I had to get them all running, and sometimes I had like really antique bytes, but no meaning of them. The way I wanted to do that was to have an assembler that would work on all of those architectures. An assembler where I could add a new architecture in an hour or 2 and then get back to the project that I cared about, instead of wandering off for 6 months to write an assembler just to finish a project that I could have done in a weekend. So now that I've wasted those 6 months writing the assembler, you can in fact add a new architecture in an afternoon. Some of the modules that you'll see here today, I wrote in an afternoon at a coffee house. I wrote on a bus out of Boston. I wrote while stranded in the Boston airport on my way back home. A couple of hours is all that it takes to take the definition of an assembly language from the book that describes it, to add that as a driver to this assembler, and then have a working assembler for that architecture with all of the fancy features you might want. Little about me, my past projects are the International Journal of Proof of Concept, or Get the Fuck Out, Do we have any readers in the audience? Woo! All right, good. I wrote a thing called MaskROM tool, where you take a photograph of a microchip, specifically of the read-only memory, sometimes preprocessor to make the bits stand out. And then this is a CAD tool that allows you to mark where all of the bits are, figure out the color difference between a 0 and a 1, and then dump out not just the bits in physical order, but also the bytes in logical order that you can then disassemble and begin to reverse engineer. My very next project will be to tie MaskROM tool into good ASM as a way to recognize when I've figured out the correct decoding order by having the assembler say that the binary looks real or not. Like, do relative branches seem to go to the entry point of an instruction rather than the middle of one? Or are function calls to absolute addresses usually going to the same region of memory as they would in a microcontroller like this? And the book that I mentioned was available from No Starch Press. It has a lot of nifty tricks for breaking into a microcontroller or a smart card when it has firmware that you would like to read, but it is configured to not allow you to read it. We have a lot of different tools today. On the disassembly end, we have very nice tools. I would have killed to have tools like this when I was starting out. Not only do we have IDA Pro with all of the fancy features and decompilers and whatnot, but we also have Ghidra at a significantly lower price point and significantly easier scripting. Lower price point for Ghidra. Binary Ninja has the lower price point, not quite so low, but much easier scripting. We have Radara 2. Some of these tools have flashy GUIs. They have tons of architectures supported. Like when you start using IDA or Ghidra and looking at the processor lists, you realize that some important customer really needed each of these assembly languages added and was willing to cut a check to get that feature tossed in. These disassemblers also have lifters. And the lifters allow us to have decompilers, and the decompilers are now getting pretty good. So that if the code was written in C, you can usually read it in something like C. On the other hand, we have assemblers. And assemblers have pretty much not advanced in 30 years. If anyone here from the NASM dev team is mad at me, we can do fisticuffs in the court afterward. Basically, NASM is the best maintained assembler, or YASM as friendly competitors, but they only work for x86 and AMD64, so you're never going to use them on like a weird architecture on the side. NAC&SM and some macro assemblers are also scriptable, but they're all generally trying to either use the output from a compiler, like the GNU assembler, or they're trying to support handwritten code in the same dialect that has been used forever on one architecture. Anything else is generally antique and unmaintained. If you want to do Z80 work, there are patches to TurboAssembler. And you can also kind of jerry-rig an assembler yourself just by doing macros and the C preprocessor. And this works, especially for the easier sys architectures, but it doesn't get you the nice features that you would like. It doesn't get you clean legible code. It doesn't let you export legible code to other file formats. And it's not easy to retarget. You would spend a lot of time adding definitions for bit fields and things that are the same across many architectures and that ought to be reused. So today I'm going to introduce you to the good assembler. The first design rule of this is that it is obscenely easy to retarget. You should be able to sit down, spend a little time reading the tutorial, and add support for any 4, 8, or 16-bit instructions that you care about, or any RISC instructions that you care about. The assembler and the disassembler are produced from the same definition. So when you're adding a new language to this, at no point are you writing any lexer or parser code ever. None of that is unique to a given architecture. This does break compatibility with other assemblers for that architecture, but it's convenient and it's consistent enough between them that you won't have trouble using it on a new architecture as soon as you get the gist of it. The output of this, you get command line tools, right? Because that's what we're going to use in our make files in order to take the assembly language for our shell code and then wrap it into whatever we're using in our exploit. There's a C++ library, because sometimes you need to recall, you need to run the assembler many different times, or the disassembler, in order to figure something out about a binary. For example, I need to run a few thousand permutations of a mask ROM through the disassembler in order to figure out which ones might be real. It's a lot faster to do that without having to fork and shell out for every call. So having it as a C++ library allows me to get that behavior generically for every language that I support without having to tie things together with shell scripts and bailing wire. I also have a REPL interface. This is an interactive shell using GNU readline. As long as you're not on Windows, it has tab completion and history and all that other stuff. The value of this is that when you're moving between assembly languages, you need to catch up on the new one. And you already know the gist of it. You might know that it's a load store architecture and that it has these register names. But it helps a lot to be able to type in a line and see the bytes of it and know that it's grammatically correct. Or to type in the bytes and then to see the disassembly to know that the bytes themselves are a valid instruction. And it supports that in the REPL interface. I also have some cell phone apps, because that's apparently what the kids are doing to study these days. And it's also a first-tier principle of this assembler that the output can include the comments. So I'm not ditching the comments in my preprocessor. I'm keeping them along. And the reason for that is that when I'm outputting code that other people will modify, I want to bring the original assembly code and the original comments along with that so that it can be read on the side. I'll show you some examples later on of how we can output a byte array in C or in Golang. I can output Yara rules, complete with comments, so I know where to put wildcards, which is very useful when I have, say, many gigabytes of satellite TV forum file attachments, and I have one ROM for a given smart card, and I want to know if anybody dumped any other ROMs for related smart cards or a different version of the same ROM. And I can do that by taking the code, converting it to Yara using my assembler, and then blinding out some of the nibbles with question marks in order to use like anti-malware stuff against my embedded targets. We're going to start with a quick demo. I'm not doing a live demo because watching someone type assembly language is boring as sin. Instead, I'm going to talk about an important part of my youth. The TI-85 was how I learned assembly language. The TI-85 is a graphing calculator. If you're in the States or France, but apparently not if you're in Germany, I forget what the borders are for this. When you were in high school, Texas Instruments convinced your high school to make you buy one of these things for $100, $120, and apparently by inflation they are still $120, even as the Z80 microcontroller is now an antique. The cool thing about this is that it was never supposed to run machine code. And teenagers figured out how to do it. There was like one dude who figured it out for the first time. He figured out that if you exported the memory backup of this, that the place where the custom menu was stored, these 5 buttons at the top, they're your menu keys. And the custom menu, you can put any menu entry in there. And the menu entries he was trying to figure out. And the first part was easy. There's a string that is in the label above the key. The other part is a pointer, and the pointers looked to all be in the same region of ROM. So he changed one of the pointers, and he loaded the backup back into the calculator. And when he called it, the calculator crashed. So later, figuring out a couple of legitimate targets, he was able to confirm that this was a function pointer. And then he needed to have a place to put his shellcode. When he first loads the backup, the shellcode could be anywhere, but this is a garbage collected basic machine, like line numbered basic. So all of the objects in RAM get moved around. And there is one exception to this. You see the graph on the screen there? You can take a screenshot of that as a bitmap, and then you can load that bitmap back onto the screen. So the frame buffer is at a consistent address. He figured out what to put into a picture variable so that when it was loaded into the frame buffer, it would be executable code with a consistent entry point. And so in order to run code on here, you first load a picture on the screen and then you jump to it. And I wanted to play around with this because what could be cooler than that? The code for that sort of stuff looks like this, and I've got it running in my assembler. I wrote a Z80 module on a bus, and I then made header files to describe the different, the different global variables and that sort of stuff. And this is in sort of the standard Emacs style for defining assembly code. So we have labels on the far left, a colon comes after a label, then you have a verb. After the verb you have your parameters. They may or may not be grouped with parentheses. They may or may not have prefixes before them. You'll see, for example, that I have an octothorpe, like the number sign, before any immediate value, like 0303. You'll also see that I have an @ sign before anything that is referring not to a value, but to the thing in memory at that address. And then labels I have no prefix for because they're unnecessary. This style is different from other assemblers that you work with, but it's close enough that it should seem familiar to you, and it's close enough that if you've got a cheat sheet of the grammar, which is in the README file, you can catch up quickly. Now, one way to get output from this is the binary output. So this is what Hello World for the TI-85 looks like in just as bytes. You'll see that it begins with hello people. It's a nifty trick they do. The very first thing in the program is a string of the name, terminated by a null byte, and the byte after the null byte is the entry point for the code. And these teenagers reinvented a global offset table and position-independent code in order to support this running on calculators with different versions of MassProm. But this is really hard to read. Like if I tell you that that first part is the menu text, you can kind of see it as you look at it deeper, but you don't see what any of the instructions are, and you won't, unless you became absolutely fluent in Z80 machine language in a way that none of us need to be. So you also want a listing output like this. And here, again, this is the output of the assembler. I still have an address on the far left, but then I start having a column of bytes, which are what I'm describing, followed by the instructions, followed by the comment. And this becomes a lot easier to follow what individual bytes mean. And I can go a step further. Who in the room uses NASM or YASM? Okay, I'm not going to yell epithets against you as x86ers. It's okay. So if I wanted to share a program that I'm writing with you, and you use NASM or you use YASM, and maybe you don't have a copy of this assembler yet because it only went on GitHub a couple hours ago, what I can do is I can produce NASM formatted text. This will build with NASM to produce the exact same binary as I had a few slides back, But I've also got comments for all of the instructions, which NASA doesn't understand because it doesn't support this architecture. It understands bytes. And if you need to patch this, you can read enough of it by going through the comments in order to make your alterations. I can also export it as Golang. And in Golang, I include not only the bytes and the comments, but I also include the symbol tables so that your code operating on it can do things like replace the 16 bytes at target address +1 with the real address that you want to fetch. You know, live modifying the shell code before sending it to the target. We'll begin by seeing how to define a NOP instruction. On Z80, it's really easy to remember. A NOP is a 0. Not only is it a 0, but every bit of the 0 matters. So you have a 0 byte, there are no parameters, there is nothing variable. Flip 1 bit and it's a different instruction. So that can be defined with this code. Spread out a bit, this is saying we're going to insert a new instruction called NOP. It is 1 byte long, its value is 0 for the opcode, and the opcode mask is FF. We also define a help string and an example. The help string I need because in my assembler, I have a cheat sheet for every architecture. If you've forgotten how to phrase an instruction, it will remind you. I also need an example instruction because I have aggressive self-testing. If this example does not assemble to this instruction and then disassemble back to itself, something is wrong and the language is invalid. Insert itself is creating the instruction, and then we're kind of appending on our help and our example and our parameters. The mnemonic is what's defining this opcode, and it might be different on RISC architectures where you might, the complicated RISC architectures like MSP430 and PDP-11, we have many addressing modes instead of a simple load store. We then, of course, have the name of the verb, the length. We have the opcode itself, and then a mask against the opcode. The help for our help table, and the example for the self-testing. This also allows for autocomplete within the REPL environment. So if I hit N and I type tab, it tells me that in this architecture, I can do either neg or NOP. And it can do the same thing for the parameters afterward if you forget the addressing modes. As you type it in, it produces the instruction, and you can also go backward. You can type in the bytes, and it will give you the instruction. You can also tell it, in addition to having like the verb there, you can tell it to add the comment automatically to the end if it's not already there, which is handy when you're absolutely brand new to an instruction set and don't yet know what the verbs mean. And then, of course, this also pops up in the help self-test, in the help menu in order to, the cheat sheet menu to let you know which operations are available to you. You can also do a self-test. You can tell it to assemble every example, then disassemble it back, and make sure that that symmetry exists and without conflict, meaning with no two instructions that overlap each other. And you can also do fuzz testing, in which you disassemble random gobbledygook and then reassemble it and make sure that that symmetry remains. We've not handled parameters yet. The way that parameters are defined here, you have immediate values. This means just a number. Absolute values, meaning I'm not talking about the number, but the thing in memory at that location. An address, which might be either linear or it might be relative. You can define it either way, and it matters how it's encoded, but it's expressed to you as a programmer the same way. You have named registers, like maybe A or X, Y, EAX if you're into that weird stuff. And we also have the same thing applying. We have indirection applied to registers. So if you have an @ sign before a register name like HL, that means that you're referring to the value in memory at the address held in the HL register. And you could do that in parentheses as well to mean that you wanted the value in memory at HL plus X. These are usually defined by your instruction set itself, so all of these should be in your programming manual for that architecture, and none of these combinations should be terribly surprising. And then you can use the auto-completion and the cheat sheet in order to know which memory addressing modes are available to you. On some architectures, for example, you can add the X index register to the register before you dereference it to find the value of that address. But the Y index register, you're just adding on to the value in the address that's exactly at the register location. Okay. So a more complicated one. This is a load from one register to another on Z80. So we have two registers defined. And these are each 3-bit definitions, meaning that I have an 8-bit byte that does my move. And the registers are a little weird here. You've got A, B, C, D, E, H, L. And each of these are defined in that order. So what I do is I just make a C++ class that describes a Z80 register. And then I use the C preprocessor to throw this into my definition. So now I'm saying that I've got my load instruction. Its opcode is 40, masked against C0, because only the top 2 bits, only the most significant 2 bits matter. By help, I say that it copies one register into another. I provide an example. LD, BB, that's a useless but legal instruction. I then define the first register and then the second register. As a convention, I usually put the destination first. Maybe God intended it that way. A lot of these instruction definitions are so old that, like x86, nobody can agree on whether the destination comes first or last. They're not quite so bad as x86 in that the floating point go in the opposite direction from the main instructions, but that's the way that it works. Now, with this LD instruction, things get a little weird in one subcase. So I have this prioritization trick. So normally, if the opcode is 40, masked with C0, everything is good. But if it's 46 masked against C7, which is a conflicting description, then I'm using an indirection from the HL register, which was otherwise not really defined. So I have this prioritize call in here. And what prioritize does is it says that the second definition is a higher priority than the first definition, so that if they conflict, there's a clear winner. If I comment that out, if I remove the prioritization and still have those two definitions, then it automatically catches that duplicate for me in the self-test, and it will refuse to run this language. And it's by using tricks like this that when you are very quickly typing as many pages out of the datasheet as necessary, don't panic about that, it's sometimes as short as 4. When you fat finger a bit mask or mistype it or something, this will catch you. And by reliably catching those mistakes, you more likely have a working assembler on the first try, and you're less likely to think that you have bugs in your assembly code that are actually bugs in the assembler. Let's see another example. Who here totally paid for all of their TV channels 25 years ago? Okay, that's good. No stitches in the room. 25 years ago, you would go into a sketchy bar, and you'd meet a very nice man in that bar, and you would give him a few $100s, and he would give you a card like this. The card that he would give you would be reprogrammed with an identity shared by a few hundred, maybe a few thousand cards, all of which had one telephone bill to the TV supplier. And this worked because back then, the TV signal was strictly one way. It was downlinked from the TV company to the TV receiver. And the only feedback was that some of these had a telephone modem that you could dial into a landline. I know I'm using words that some of the kids here don't understand, but trust me that these were real things. And then it could call home in order to add a balance of pay-per-view credit. You would pay to watch TV shows, kind of like streaming, but more depressing. So this particular card, and there's another card that looks like it but has a different instruction set. I'm talking about the F card here. Internally, this is a Motorola 68HC05 chip, except that some of the bits are scrambled. The opcodes are not compatible. Parameters are not scrambled. Parameters go just in the normal order. So one of the things that I really wanted was to be able to take, say, my 6805 language module, inherit from it, and change it so that I could deal with cards like the F card with very little code. So my buddy Chris Gerlinsky sent me a tweet. And he said, he was quoting like a TV crypt message from 1995. And this is the only description that I started with of how the scrambling works. He says, only the opcodes are scrambled, not the operands. The bit order from most significant to least is 7645312. And then the most significant bit is flipped. Now, you'll notice something. This is actually symmetric. If you run this twice, like XOR, it goes back to the beginning. And then he tells me that I can see this in the die photos. So here is my implementation of the scrambling. And I'm basically just copying his tweet into my code. Here is a picture of the relevant part of the die. We'll all have a moment of silence for the poor card that I boiled in acid to get this. You can kind of see like the serial number up here in the top right. The wide horizontal lines that you see, that is the memory bus coming into the CPU. There are these very faint vertical lines behind them. 8 of them matter. There are a few more just because it's a busy chip. Those vertical lines are the input to the instruction decode latch. On this architecture, the opcode is only 1 byte, and it is only the first byte. So what this latch does is it holds that byte, and it doesn't let go of it until it's ready to fetch the next instruction. One of the ways that they would hack this architecture with probe needles is they would force these bits low in order to make it never do a branch, and then kind of let it run through all of memory while moving a needle from bit to bit in order to read the memory out like a bit of significance at a time. In any case, here's a close-up of it. Can you all see the horizontal wires that are the input from the instruction, from the memory bus? These are the data lines. Address lines are elsewhere. Okay, and can all of you see the faint vertical lines behind them? They're like a slightly darker color and they overlap. Okay, so these are the vertical lines. These are the columns that go to the instruction decoder. The most significant bit is on the far left. The least significant bit is on the far right. So 76543210, exactly in order as we would expect. These are the row lines which come in from memory. Here, 0 is at the top, 7 is at the bottom. Okay? I'm going to flip back and forth a bit just so that you can keep the pattern in your head. These are the points where they tap. And this is what does the scrambling. The inversion is a little bit elsewhere. But this describes all of the bit scrambling. And so then Chris sends me another tweet. He says that on this card, on the F card, I can send these 5 bytes and then these 92 bytes, and then it will dump out all of its EEPROM to me, and I can know the identity of the card. Now, I don't actually give a damn about the contents of the EEPROM because these cards have not worked for TV reception in many years. But I do give a damn about shellcode because I want to experiment on these cards. And to experiment on them, I want to run code on them. And if there's an exploit that reads EEPROM out of the serial port, I can patch it to read whatever else I want. Like a copy of the mask ROM in order to understand what the programming of this card is. So I wrote the one page of code to do the scrambling. My assembler now supports an F-card language. And when I run the disassembler on the bytes that Chris sent me, you can see that a lot of different things start standing out. Like, there are a lot of 2Ds. This is an OPSLET. The JSR, that's a jump to subroutine in this architecture. You see how those two addresses are so close to each other? Like 1E7F and 1F31? Those are functions in mask-ROM, and these happen to be at the location that in that architecture mask-ROM should be at. So this is telling me that I now have valid code, and that's valid code that I can patch. I'm also noticing that it is doing a load accumulator from address 88 hex, and then a store accumulator from address 88 hex. Which means that this is a global variable that it's loading into and then moving out. So this is real code, and I can now read it. And then I can begin assembling code for this architecture and writing my own variants on the exploit in order to explore different parts of the card. Isn't that a nifty trick? And this is for one page of code without being dependent upon any other pieces of that architecture. If I need to add new languages, I can sit down and I can define them. And then if I really need to, I can also run this on iOS and on Android, because the whole thing is written in Qt 6, and it's a piece of cake to throw that in with a little GUI and flush it down into the thing. You would never do this for developing machine language, but you would absolutely do this in a coffee house in order to study it with pen and paper. You know, like when you're studying a foreign language and you use Google Translate because you can't remember the word for a beer or something. Now there are a couple of things that don't work here. The first is x86 support. If you want x86 to use NASM or YASM, they've been dealing with that hell of an architecture for far longer than I care to. I do intend to add, at least through the IBM XT and AT, like the 8086 and 8088. The trouble with x86 is that it is complicated even by 1970s standards. You have prefix bytes, and a prefix byte changes how the instruction after it is interpreted. After the prefix, which is optional, you have the opcode. Now, in every other instruction, your parameters are relative to the opcode, but not on x86. Because in x86, after the opcode, you have the mod rm field. And the mod rm field contains all of your target registers and any additions to them, and all of the complicated addressing modes that you can do in x86, except for segment overrides, because those are handled by a prefix. All of that fits into the mod rm field, and that field is variable length. Any other parameters happen after the end of the mod rm field, which means they can be relatively addressed from mod rm itself. And this gets complicated. And I know that after this lecture, one of you is going to come up to me and tell me about how fucked up things got in the Pentium era, and that it somehow got worse in AMD 64. These can all be added, but a new assembler is desperately needed on everything except x86, and not necessarily for x86 itself. RISC-V for ARM, all of these things are easy to support. I also don't do very much with macros or things like arithmetic. In NASM, for example, when you have a parameter that does addition, you might have an infix plus operator. You might also do it when you're trying to do things like adding two symbols together. That's an entirely different grammar from the assembly language itself. And in my current parser, I don't have support for that, specifically because it's a second language hidden within the first. At some point, I'll probably add it in, you know, maybe within curly braces or something. It's just a different parser. And finally, I don't really have a linker here. Linkers and loaders are beautiful things, but they're very complex things. And if I were to do them directly within the assembler, I would kind of paint myself into a corner. I would be stuck with particular linker and loader formats. We have excellent complex systems. We have ELF, we have Dwarf, all of the descendants of COF and XCOF and that sort of stuff. None of which are really that appropriate for microcontrollers. We have linker scripts, like for GNU-LD, which are designed for desktops and then somehow straitjacketed to work for microcontrollers. At some point, I would like a linker intended for messing around and intended for weird embedded stuff. And I think that would not be terribly hard to write, that it could be very effective, and that it might replace GNU-LD in microcontroller programming, where extra features are handy. And where simple scripting, where you can do things like define a structure at a location, maybe your interrupt table, things like that. This could be rather awkward to redefine when you're forking the GNU-LD examples for GCC targets. And they needn't have that much complexity. They can be described in a much simpler way. Cool. So that's it for my assembler. If you'd like it, here's the GitHub address. It's been public for an hour. Are there any questions for me, folks? No one's walking out because of my x86 jokes? That's good.
What are some processors you already support?
Great question. So when I was writing microcontroller exploits, I was toying around with a bunch of old instruction sets. And some of them, like 6805, are becoming less popular, but are still widely supported. 8051 is the same way. Some of the others were very, very rarely documented. Like one of them is a Toshiba instruction set called TLCS47. It's used in the ancestors of today's microwave, like oven control chips. I have never been able to find a single program in that machine language except for the one whose die I photographed. I thought I found a counterexample, which is in the manual. There is a picture of Baudot tape, like the 5 dots on a paper tape that would be used in teletypewriters. And I decoded that hoping that it was real code, and it was not. They were tricking me, and it was the same clip art that they used in every other chapter of that book. I also added support for the EMZ 1001, which is a clone of the AMI S2000 chip, and the only reason anyone should care about it is that it is the only microcontroller domestically produced in the former Yugoslav republics. It was made in Slovenia. And a Slovenian museum sent me one of the chips and asked me to rip the mask ROM out of it. And I did that, but then I needed to read it, so I had no assembler yet. By adding that definition, I now have it. I also support more common ones, like the 6502 that is used in the Atari VCS, the 8051 that is in like every keyboard and mouse you've ever purchased from a sketchy vendor, and SM83, which is the instruction set on the Nintendo Game Boy. So I've got examples for Atari game cartridges, for Game Boy game cartridges, all of which you can build and then run in emulators. The real value of this, though, is not so much the languages that it already supports, but that if you have a project in an instruction set that is not supported by any assembler, you can add support to this assembler in a couple of hours and then get back to the project that you actually give a damn about. And this will save you from doing pen and paper assembly, as I did when writing my 6805 exploits. I really wish I could have skipped that pain. Especially because if you properly disassemble the exploit from this book, the one in the Nipper is a Buttlicker chapter, the jump instruction has the wrong target. It's off by 2 bytes, because I made the mistake with pen and paper. The code still works. There's just a knot that could have been a different byte had I known. So adding new instruction sets is definitely where the value is here. Any more questions? With the lighting, I can only see half of you, so holler if I'm not seeing it. All right. Thank you kindly, and I'll see you next.
Glad we came back. Sorry? Glad we came back. Yeah.
Oh yeah, we were just wondering if we might
Like automated technical and stuff.
These guys have super eager.
I know the first time. Yeah. You know there's like those smart cars, like they have some tiny chip that like some power goes into it, like checking identity or stuff.
Can I get my one?
But there's a credit card? And like, I'm not setting up there. Basically, like, whatever you get, like, code in, we're buying bus taxes. A lot of those actually looks like a getting better. Like, fancy, credit card, actually running Java card. Oh, yeah. Yeah. The Java card
Yeah, there's also interesting when he was talking about like why x86 is such a big
Yeah. Have you seen me tell me like how they even design the layout? Oh, it's a nightmare. They have to like I struggle with